It's the last session of a wonderful week. And I want to thank Katie and Simone for the organization. Absolutely wonderful. For me, it was very inspiring and educational, I have to say. So let's continue with our first speaker this afternoon, Sui Tang. And I'll let you read the title.
Yeah.
Please.
Yeah, thank you for your introduction. So first of all, I would like to thank the organizers for such a wonderful program, and especially for Katie and Simone for organizing this workshop to bring us together. I really enjoy my stay here. It's my great pleasure to speak in this workshop. I'm going to talk about learning interaction kernels in stochastic systems of interacting particles. And this research, is partially motivated by the birds watching in the sky. And we also acknowledge the support from NSF and UC Santa Barbara. And this talk is based on a joint work with Fei Lu and Mauro Maggiani from Johns Hopkins University. Okay, so recently, the rapid advancement in data information technology and computation actually have inspired extensive research effort towards the data-driven discovery of dynamic systems. And for example, how to fit weather data into a dynamic model to make numerical predictions, and how to model the motions of robots, and also relevant system identification problem in control theory, and as well as how to understand mechanism of infectious disease, such as COVID-19. So all of these questions involve extracting governing equations or laws from data. So in this way, we can have an interpretation about underlying dynamic system and make predictions and simulations. And many of you may have seen this example in the textbook of calculus. Like this system considers a single pendulum, and we are taught how to derive the governing equations for this simple system. However, this is not the case in many practical scenarios, and the system are typically very high dimensional, and we only have very limited physical knowledge, and we have complicated data. So this actually imposes greater challenges to tackle this problem. And recently, there's a lot of effort from applied and computational math community, as well as machine learning, to propose different approaches to tackle these problems. The examples such as Sandy algorithm, like using ideas from the sparse regression, and also the approach inspired from deep learning, like physics-informed neural networks and the PDE. And in particular, the Washington matrix has been applied to analyze the time series data. In fact, Yunan on Tuesday, she gave a very interesting talk on how to use optimal transport to learn chaotic dynamics from data. And we also see a lot of workshops coming out recently, trying to bridge the machine learning, physics science, and dynamic system together. So we can expect a lot of exciting work will come out. Okay, in this talk, actually, I'm not going to discuss the learning strategy for arbitrary dynamic systems. I'm going to focus on the spatial family of it, like called interacting particle systems. And they are very, very common in our daily life. And here are a few examples. So if each example, actually, we see here the moving objects as moving particles, and the interact and display a variety of behaviors. It is a non-standing science problems that to find the individual interaction rule that are responsible for these collective behaviors. And this kind of problem has attracted continuous attention. Maybe dates back to the age of Kepler and Newton, and extensive research effort has been made. And in this talk, actually, I'm going to present a family of first-order stochastic system of interacting particles with pairwise interactions that have been extensively studied in the literature and trying to describe the motions of these interacting particles. And here I want to be as general as possible. And suppose we have n agents, x1 to xn in RD, they interact according to this form of governing equation. So in the drift term, we may have an external potential as well as the pairwise interaction governed by the kernel Ki prime. And we also have a diffusion term here, sigma, and modeling the random effects. And there are remarkable progress on quantitative analysis, qualitative analysis, as well as a numerical analysis on this type of governing equation, as well as the mean filter limit. So it has wide applications in modeling the opinion dynamics, particle dynamics, and swarming dynamics. We also see the applications of this type of equation in the previous 2 workshops in this program, like sampling and optimization. And in our workshop, actually, Franca and Tedo talk about their application on yesterday's talk and make a very nice summary. And here I'm very lazy. I don't list the relevant literature here. So far, the majority of the work, these terms in these governing equations are predetermined. If we consider, say, if we want to apply these governing equations to match the real life data, and then this will inspire us to consider the fundamental problem. Like suppose we have data generated from the governing equations. What are the data-driven methods that can allow us to derive estimate of these terms in the governing equations? Oh, yeah, that's true. Thank you for pointing out. Yeah, because I write it as xi prime and xi. That's why I say it's RD times RD, but now I changed to the minus sign. So yeah, thank you for pointing out. That's a typo. Okay, so recently there's a lot of work towards the data-driven discovery of interacting particle systems. And here is of course, a non-exhaustive list. And I believe people from various backgrounds have made contributions to this type of problem. And here I mainly put the work in 2 categories. And the first one is the parameter estimation. I also call parametric inference problem. And typically, according to some prior physical knowledge, and learning governing equations reduced to learning some unknown parameters like vectors in the system. And then given the data, and the people will construct objective function involving solving this PDE constraint or SDE constraint optimization problem to get estimators of this unknown parameters. And for example, the diffusion estimation, here the people consider how to infer the diffusion constant from a partial observation of a large scale particle system. And there's a lot of recent work on drift estimation in both linear system and nonlinear system, with application, for example, to the cloud dynamics. And here I want to mention some work in statistics, people do exploratory data analysis. They really use the stochastic interacting particle system to model the animal swarming behavior, as well as doing the sports data analysis. And for example, David Brenninger, I mentioned him here because he is a statistician working here at UC Berkeley. And in the past few years, our group has worked on the non-parametric inference and also solved this problem from the perspective of inverse problem. So compared to this previous work, we don't assume any parametric form of the unknown terms in these governing equations. And the majority of work has been done in the deterministic setting. And as Yuna mentioned in her talk, for the inverse problem, we have to consider when the data have noise. And the first situation is the data has measurement noise. And the second situation is that the system has intrinsic noise. And of course, the third situation is that they have both intrinsic and extrinsic noise. So this actually motivated us to extend our work to first consider the situation we have the intrinsic noise. So we consider this a problem in the stochastic setting. And in general, this problem could be very difficult. Just as what we did before, for the determinant setting, our starting point to investigate this problem, starting with the pairwise radial interactions. So here we make a very specific assumption about this interaction form. So you have a phi acting on the pairwise distance and times the pairwise difference in position. And in the compiler form, actually, we can represent this f only depends on phi. And it is a gradient of an energy function, only dependent on pairwise distance. And this phi is relevant to the derivative of the energy function. And in this kind of system, and the dimension is still dn, but we have a very simple interaction rule, the dimension is only 1. And nevertheless, this kind of system and its variants can still generate a variety of collective behaviors, and so widely used. So I would say numerical examples of this kind of systems in many speakers' talks, like Katie, Jose, and Yuan's talk. I believe Yongxin will talk about the application of intelligent particle system in control theory. If he's going to show any numerical example, I just make a prediction. He may show some example involve the radial interactions. I'm not sure I'm correct. Let us see. Okay, so now I'm ready to make the official statement, problem statement. So here, as I mentioned, we don't want to do the parametric setting. So what we know here, the prior knowledge, is that this phi, like here, for example, is a one function, like has a bounded derivative. And I mean, if we know this, and then we know this SDEs where post has unique strong solutions. And also we assume sigma is known. And the training data here consists of the observations of this xt at some time window, let's say 0 to capital T. And we can choose uniform time instance or non-uniform time instance. And we also consider the case that we may have trajectory data collected from different replicates of the system. So we are observing the system at starting with different initial conditions. So here is a visualization of the data regime. So now, suppose like we observe this kind of data, can we actually construct some method that give our estimator phi hat that is close to phi? And because we know phi is relevant to the energy function, so they give us the physical insights, and also we would like to use phi hat to make meaningful predictions and simulations on larger time interval. So these are the goals we want to achieve. And this problem setting is exactly the stochastic extension of our previous work for deterministic system. Okay, so in fact, this kind of knowledge problem belongs to a spatial instance of the statistic inference for SDEs. So this is a very well-established area in mathematical statistics. And we first read the literature, like what the work people have done there. So we found out actually the non-parametric drift estimation in high dimension SDE is very challenging, both theoretically and numerically. And here, suppose to have a drift function bxt in the general form, and then we want to infer it from the trajectory data. The majority work has been done when the SDE is ergodic and considered a single trajectory case. As long as the dimension is bigger than 2, then the sense becomes very challenging. And we don't have found many like literature in this direction. We know that, for example, Dalayan and Reis gave the first convergence rate of these estimators back to 2007 using the kernel type estimators. And the non-statistical optimality results has been established in the very recent paper by Nick and Ray. And they show this kind of rate is optimal in the L2 loss. And you can see that even here, this dn is going to be cursed by the dimensionality dn. So that's kind of, if this B is very high dimensional, you need a lot of data actually to recover this B up to a certain accuracy. And compared to the ergodic case, really a very few work in the non-ergodic case. And unfortunately, our interacting particle system is never ergodic. And so we consider in this non-ergodic case with multiple trajectory data, we also find a recent work by Comet and General Catalot trying to tackle this problem in the 1D. Still, they obtain some convergence rate and no optimality result has been achieved. And our work actually fitting in this setting. We have a in general, the dimension is dn not equal to 1, but we have a simple interaction rule dimension of phi equal to 1. And we are trying to say what's the available learning strategy for our case. So I was told that actually when we try to tackle this problem, the first approach I should try is the maximum likelihood estimation. We should understand when it works, when it didn't. If it didn't, think about the variance. So what is the mathematical foundation for this maximum likelihood estimation is a Gasanov theorem. So this theorem has been mentioned many times in this workshop. So here I give a very simplified version about it. So suppose we have a SDE like this, and let's say P sigma is the probability measure induced by the true solution driven by B. and the B sigma is the law of the respective driftness process, namely B equals 0. And as long as the noise is non-degenerate and also B fulfills some conditions, and then the Gaussian theorem actually tells us a way of computing the likelihood ratio between the of the measure generated by the true SDE and with respect to winner measure. So how to understand the quantity? It's like we can interpret it as the probability of seeing trajectory if the underlying system is driven by B. And based on this Gaussian theorem, of course, for first the approach I want to try is that in the continuous time setting. So here, suppose we collect data from different applicants, and here is the error function for the path, for the mth path x0t to the m. Let's say we consider any potential candidate function, like phi here, which I highlighted in the blue color. So this, I calculate the negative log likelihood of this error functional. So this is actually represent the probability of seeing the trajectory if the system is driven by the phi. Now we are given like data collected from m independent trajectories. So we take the sum. So this quantity actually is a negative log likelihood of saying the m trajectories if the system is driven by phi. Now we want to maximize the probability of seeing the trajectories, which is equivalent to minimize the negative log likelihood here. So that's why we say this is a maximum likelihood estimators. And given this error function, you see this is quadratic and very efficient to compute. And we choose a very simple hypothesis space, trying to minimize. And in this way, we get an estimator phi hat. And for example, we use piecewise polynomials like splines and wavelets to do this. And of course, this is a continuous time, but in practice, we only have discrete time. So how to do that? Okay, so here we consider like we use the Euler-Maruyama to give an approximate likelihood. Of course, some higher order methods may be used, and we use this because it's simple. It's really simple, and it preserves the structure of this error function is still quadratic, and we can solve it using the least square. Okay, so this story, and also we solve this minimization and by forming the normal equation in a parallel fashion, and then we use the pseudo inverse to find out the coefficient. And here is the computation cost involving how to form the normal equation and how to solve this normal equation. Okay, so how does it work? And we test this approach on several prototype systems, and this is maybe one of the most simple example. And so this dimension is 10, and they have 10 opinions in the system, and we observe the system at multiple times. And if here this m equal to 32, and we have the noise sigma equal to 0.1, and here this blue curve, this black curve is true, and the blue curve is estimator. You can see that it really fits pretty good. And if we actually increase the data size, and of course we achieve better performance. And also we test like the case when we increase the noise level, and still we're doing pretty good job. We can actually identify these opinion interactions are heterogeneous. And we also test their ability in prediction the trajectories. So you can see that we take like measurements from a very tiny interval, 0 to 0.5, and we'll make predictions on 0 to 50, and both on the training data and make the prediction as well as on the new data sets, and to test the generalization ability. And all of them doing a very good job. Okay, so now we just test like several numeric examples. We really want to have a fundamental understanding to say when this MLE approach work, when didn't. Okay, so how to tackle this problem? So in the classical literature, people concerned about the estimator of this Fv, like treated as a function B I mentioned in the previous slides. And here we are interested in analyzing how the estimator of phi denoted by this symbol. So we are more like in the inverse problem setting because the phi is a latent function hidden in this high dimensional field. And of course, there are several asymptotic regimes we could consider. And here we'll consider MTL fixed and M goes to infinity. And to tackle this problem, we need to find a matrix to assess the estimation error. And also for the inverse problem side, a fundamental problem is trying to address the identifiability problem. If we have like infinite data, can we actually uniquely determine this fit from the data? Otherwise, the estimator learned from finite data have very limited value as a scientific and prediction tools. And also we concern about rate of convergence, which is a fundamental study in the statistical inference. Like this kind of question is to address, okay, if we have some, we want to achieve some estimation error up to a certain accuracy epsilon, how large M and HM should it be such that we can achieve this task? And lastly, we want to also do some analysis on the trajectory predictions. So these are the fundamental questions I want to address. Okay, so the first step for the evaluation matrix, we actually extend our work in the deterministic case. We introduce a probability measure on the pairwise distance. And here you can see this Dirac defined on the pairwise distance between the agents at a time t. And then we take the integral and we take the average. We have entries 2 pairs, and we take average over the t because we observe the dynamics from 0 to capital T. And then from this probability measure, we actually introduce a mean squared error, which I defined here. And we introduce an additional factor R here. This is to incorporate the structure of governing equations. It looks like very abstract, but here, if I think carefully, I think this is really a natural matrix to consider in our regime. Because according to the structure of equation, this phi, this energy function depends on pairwise distance. So we are only able to learn this phi at the regions explored by this pairwise distance. And here in this figure, I use the orange histogram to represent the density of this rho t. And you can see that in a very short time, due to the randomness of initial condition, and it can actually explore a pretty large region. So we are able to learn this phi on this region. And also you can see from here, we don't know that good at the locations near 0. So you can see back to here, if I equals 0, we have very little weights if we consider R push rho t. And so that's why how we lose the information here. And of course, if this one here is the density axis, and in this case, we have 0.3.5. If we actually have a larger noise, you can see that this noise actually smooths out this density plot. So in the case of large noise, we have larger fluctuations at these locations. This also may saying that this weight is fewer than the previous one. This also gives some explanation. And another reason is that this error matrix also promote the trajectory predictions. Suppose we have found an estimated phi hat minus phi in this estimation error. Here is 0, and then we almost can this phi hat and phi can generate the same trajectories up to time t almost surely. So that's why I actually want to promote use this evaluation matrix. So also for the identifiability, and we propose some cohesivity condition. And for any hypothesis space we used here, we need this kind of inequality to hold. So you can see here, this is some energy of this interaction force field. We hope that it's bounded below by a positive constant times this L2 error, L2 measure of L2 norm of this phi here. So why is that here is that, so this intuition comes from that in the when the data is infinite and we have expectation of the error functional. And this cohesivity condition actually yields the following equality. You can see clearly here, if we find some var phi which minimizes error functional and which achieve the same value with phi, then this var phi equal to phi in that L2 space. And this inequality of course holds more generally on any like hypothesis space. So the intuition is that smaller the risk of functional and closer the estimation is to the truth. So, and if we do, if we assume this cohesivity constant is right, which viewed as a stability constant of the inverse problem in the infinite dimensional setting, then we're able to prove the convergence of estimators for the continuous time observation. So here, assume we use any kind of sequence of linear spaces. Here we'll assume it's C11, so the first derivative is Lipschitz continuous, and assume that this Ln has a linear growth on this hyperparameter n, and assume like the approximation power given by Ln is measured by n to the negative s. And here we'll put additional constraints on this hypothesis space we use. We assume that it satisfies the Markov Bose-Stein inequality. So this type of inequality are often used in the inverse approximation theory literature. And this setting, if we have like data collected from M trajectories, we can select this n scale as this number. So it depends on the number of data we have, as well as the regularity. Then the rate of convergence is 2s over 2s plus 1. So it's equivalent to a one-dimensional non-parametrical regression rate established in statistics. So here I want to say 3 is not too restrictive. Actually, it has been proved in approximation theory that it holds for many like function space, like polynomials, trigonometric polynomials, spline space, wavelets, and more recently rational functions. And for example, if we know this phi is like in this space CK alpha, so this is the case derivative is Holder continuous of order alpha. And then we can use the polynomial splines of degree s-1 with uniform knots. And then we'll obtain the min-max rate in M, the same as the in the parametric setting. And So, and the main gradients are proved here. We use the Bose-Stein inequality of unbounded random variables involving the stochastic integral, and based on interformular. And we actually leverage the Lorentz argument made in this paper in the non-parametric regression setting to our setting. And this Markov Bose-Stein inequality actually help to obtain the uniform bound in the covering argument to control the variance error. Okay, so our results are supported by numerical findings. So I only have a few minutes left. So actually, this is only the baby step for the SDE. There has many open problems. And here we only show that this MLE works well when this delta is small. And we can do parallel implementation, and we can have strong consistency, and we have 1D min-max rate of convergence. And if this delta t is sufficiently large, we're in trouble. So in the paper, we show that actually this estimation error is going to be bounded above by square root of delta t. And you can see this is a plot. And from the blue and the pink, we have larger and larger delta t. You can see it will flatten the curve. Really, the method didn't work when delta t is pretty large. So that's why, like for the future work, we say what's the learning approach when delta t is big, non-frequency data, as well as for the other asymptotic regime like n goes to infinity. And what if like we both have m and t goes to infinity? And here we show very promising like plots, like showing the desired rate here. And also, what about learning from a gradient data, learning from the random measure as discussed in Yunan's talk, and the multiple interaction kernels and the second order system. So there are many open questions. So you're interested in this kind of problem, please let me know. Thank you for your attention.
Thank you so very much. Any questions? Yes, go ahead.
Thank you. That was great. I have a question. So what about the problem when you have to learn the diffusion part, the volatility, let's say, because here you use your sign-offs and this works great when the DBT term is kind of like the same. But do you have any ideas what to do in case you also want to learn what is in front of the DBT?
Oh, I think that's a great question. So here, for this diffusion estimation part, I read the literature. I found like the people typically use the quadratic variation techniques to tackle it and assume like we need to have like full observation of this data. And so far, the only work that I found that actually deal with the partial observation where any like variance is actually listed here. And for general, I think this problem could be very difficult. I don't know how to do it. I found a very, very scarce literature on here. So this is the only paper I found out for estimate the constant diffusion. if you have more difficult like diffusion, like the color noise, I believe a more difficult like method has been proposed. Yeah.
Very nice thought. I have a question regarding the how to say that egodicity. So you were saying there's a difference between the
Yes,
so
exactly.
Ergodic one is easier or
exactly. So that's a very good point. Actually, this system I consider here is never ergodic. But you know, just in terms of learning this feat, we don't need this whole system to be ergodic. We just need to consider a relative position systems.
Yes.
Is ergodic, like ergodic in the pairwise distance. That may be fair enough for our learning purpose. So we observe that in our numerical experiments that we are trying to explore, like if we change the coordinates to the relative position system, that system could be ergodic, and we can learn this feat very well. So that's a very good observation. Yeah.
Okay, thanks.
Quick question, if otherwise we can take it offline afterwards.
Yeah.
Okay, I think let's thank our speaker one more time. Thank you very much.